Welcome to Session 10, Probability, Complements, and Expected Frequency. Probability measures chance on a scale from 0 to 1, where 0 is impossible and 1 is certain. Across 10 examples, we will count equally likely outcomes, use complements, convert observed, frequency to probability, predict long-run counts, compare probability forms, and reject impossible probability claims. Define the sample space, confirm whether outcomes are equally likely, compute the ratio, and check that the result lies between 0 and 1. Example 1. A fair six-sided die is rolled. Find the probability of rolling a number greater than 4. The probability scale locates each chance between impossible and certain. Plan. List equally likely outcomes and count favorable ones. Step 1. The sample space is 1, 2, 3, 4, 5, 6. Step 2. Outcomes greater than 4 are 5 and 6, giving 2 favorable outcomes. Step 3. Compute 2 divided by 6 equals 1 divided by 3. Step 4. The probability is 1/3, about 0.333 or 33.3%. Quick check. The answer lies between 0 and 1 and reflects 2 of 6 equally likely faces. This matters in real life because games, quality checks, and simulations all begin with clearly defined sample spaces. Example 2. The probability that a scheduled train is late is 0.18. Find the probability it is not late. The probability scale locates each chance between impossible and certain. Plan. Use the complement rule because late and not late cover all possibilities. Step 1. Write P nothy late equals 1 P late. Step 2. Substitute 0.18. Step 3. Compute 0.82. Step 4. The probability the train is not late is 0.82 or 82%. Quick check. The event and its complement sum to 0.18 plus 0.82 equals 1. This matters in real life because commuters use on-time probability when comparing travel options. Example 3. A machine produces a defective item with probability 0.03. About how many defects are expected in 2,000 items? The key quantities are organized before the arithmetic begins. Plan. Multiply probability by the number of repeated opportunities. Step 1. The defect probability is 0.03 per item. Step 2. There are 2,000 produced items. Step 3. Compute 0.03 times 2,000 equals 60. Step 4. About 60 defective items are expected in the long run. Quick check. 3% of 2,000 is 60, but an actual batch may be somewhat above or below that count. This matters in real life because manufacturers use expected frequency to plan inspection and warranty reserves. Example 4. In 250 deliveries, 35 arrived late. Find the experimental probability of a late delivery. The key quantities are organized before the arithmetic begins. Plan. Divide observed successes by the number of trials. Step 1. Treat late as the event of interest. Step 2. There were 35 late deliveries out of 250. Step 3. Compute 35 divided by 250 equals 0.14. Step 4. The experimental probability is 0.14 or 14%. Quick check. Multiplying 250 by 14% returns 35 late deliveries. This matters in real life because logistics teams update performance estimates from observed relative frequencies. Example 5. Classify each probability. Sunrise tomorrow, drawing a red marble from a bag containing only blue marbles, and a fair coin landing heads. The probability scale locates each chance between impossible and certain. Plan. Use 0 for impossible, 1 for certain, and 1/2 for an even chance. Step 1. Under the ordinary model, sunrise tomorrow is treated as certain, so its probability is 1. Step 2. A red draw from an all-blue bag is impossible, so its probability is 0. Step 3. A fair coin has 2 equally likely sides, so P addies equals 1/2. Step 4. The classifications are certain, impossible, and equally likely. Quick check. All 3 values, 1, 0, and 0.5, fall within the probability scale from 0 to 1. This matters in real life because probability language helps distinguish certainty, impossibility, and uncertainty in everyday decisions. Example 6. A spinner has 4 sections, but one section covers half the circle, and the other 3 share the remaining half. Can probability be found by counting sections alone? The circle shows outcome areas, which determine probability when sections differ in size. Plan. Check whether outcomes have equal physical areas and therefore equal chances. Step 1. There are 4 labeled sections, but they are not equal in size. Step 2. The large section covers 1/2 of the circle. Step 3. Each small section covers the remaining 1/2 divided by 3, or 1/6. Step 4. Counting one section out of 4 would incorrectly assume equal likelihood. Quick check. The probabilities 1/2 plus 1/6 plus 1/6 plus 1/6 bump to 1. This matters in real life because risk models must weight outcomes by their actual chance, not merely count their labels. Example 7. A weather forecast gives a 65% chance of rain. Express it as a decimal and fraction in simplest form. The probability scale locates each chance between impossible and certain. Plan. Convert percent to decimal by dividing by 100, then write the decimal over 100 and simplify. Step 1. Compute 65% equals 65 divided by 100 equals 0.65. Step 2. Simplify 65 divided by 100 by dividing numerator and denominator by 5. Step 3. The fraction is 13 divided by 20. Step 4. The reforms are 65%, 0.65, and 13/20. Quick check. Compute 13 divided by 20 equals 0.65 to confirm equivalence. This matters in real life because forecasts and insurance reports often move among percent, decimal, and fraction forms. Example 8. Which event is more likely? Probability 0.42 or probability 3/8? The probability scale locates each chance between impossible and certain. Plan. Convert both values to the same form before comparing. Step 1. Convert 3/8 by division. 3 divide 8 equals 0.375. Step 2. Compare 0.42 with 0.375. Step 3. Since 0.42 greater than 0.375, the first event is more likely. Step 4. The difference is 0.045 or 4.5 percentage points. Quick check. Both probabilities are below 0.5, but one can still be more likely than the other. This matters in real life because comparing risks requires common units and forms. Example 9. A report claims a probability of 1.18 for one event. Diagnose the error. The probability scale locates each chance between impossible and certain. Plan. Apply the fundamental bounds for a probability. Step 1. Every probability must satisfy 0 is at most p is at most 1. Step 2. The value 1.18 is greater than 1. Step 3. It would represent 118%, more than the entire sample space. Step 4. The value is invalid as a probability and the calculation or label must be checked. Quick check. Counts can exceed 1, but a probability after division by the relevant total cannot. This matters in real life because boundary checks catch reporting and spreadsheet errors immediately. Example 10. A fair coin is flipped 20 times and lands heads 7 times. Does this prove the coin is unfair? The probability scale locates each chance between impossible and certain. Plan. Compare short-run experimental results with theoretical probability and allow random variation. Step 1. The theoretical probability of heads is 0.5. Step 2. The experimental probability is 7 divided by 20 equals 0.35. Step 3. A short sequence can differ noticeably from 0.5 by chance. Step 4. The result alone does not prove unfairness. Many more controlled trials would be needed. Quick check. Increasing the number of flips usually produces a more stable estimate of the long-run probability. This matters in real life because quality testing uses large trial counts before concluding that a process has changed. Session 10 Recap. For equally likely outcomes, probability is favorable outcomes divided by total outcomes. A complement is 1 minus the event probability. Expected frequency is probability times number of trials. Experimental probability uses observed successes divided by observed trials. Quick check. An event has probability 0.2 and is repeated 150 times. What is its expected frequency? 0.2 times 150 is 30. About 30 successes are expected in the long run, but the exact count can vary.